Hello and welcome to The Space Above Us. Episode 78, Space Shuttle Flight 11, STS-41C. How to catch a spaceship. Eventually. Last time, we talked about STS-41B, which is most notable for being the first flight of the Manned Maneuvering Unit, or MMU. Bruce McCandless and Bob Stewart each flew the device over 300 feet away from Space Shuttle Challenger, with Hoot Gibson snapping a photo of McCandless that became one of the most famous photographs in history. But in addition to making an inspirational photo, the mission also proved that the MMU could be counted on for the demanding mission that was next on the docket, and the one that we'll be talking about today, STS-41C. There is a lot going on with this mission. It's actually the first time since the Skylab episodes that I seriously considered splitting an episode in two. But no, if I start doing that again, then we'll never get through the shuttle program. To give you an idea of how much we have to cover, this is the only mention that I will make all episode of the more than 3,000 bees riding along on Challenger's middeck for this flight. 3,000 bees. Before we can really talk about STS-41C, we need to rewind the clock 4 years back to 1980. On February 14th of that year, the Goddard Space Flight Center's Solar Maximum mission was lofted into low Earth orbit on a Delta 3910 rocket. Its mission? To study the sun by precisely pointing an array of specialized instruments at our local star. As the name implies, its launch was to coincide with the high point of the 11 or so year cycle of activity exhibited by the sun. By studying the sun's behavior at the peak of its dynamic activity, the hope was to better understand both how stars work and also how to better predict space weather, since solar activity has a huge influence on satellite operations. As you'll recall, this was a big area of focus for Skylab, which was originally aiming to launch early enough to catch the previous solar cycle. Skylab was a little late, but NASA lucked out and still managed to catch some solar flares during the sun's quiet period. Once the Solar Maximum mission, or SMM, was safely ensconced in orbit and its instruments were checked out, it got to work returning a wealth of data that was impossible to collect from the ground. Everything was going great, until 9 months into the mission, when ground controllers suddenly lost control of one of the attitude control reaction wheels. These are basically big heavy wheels that are kept spinning at high rates using electric power. If you speed them up or slow them down, a torque is imparted onto the spacecraft, rotating it. By placing 3 of them perpendicular to each other, roll, pitch, and yaw, you can point the spacecraft anywhere you like. This is especially great because where propellant for attitude control thrusters is a finite resource, the wheels are powered by electricity from the solar panels. So as long as the wheels don't break, they can basically go forever. SMM had 4 of these wheels, for roll, pitch, yaw, and skew. If I understand correctly, the skew wheel was diagonal to the others, and was there to help in case one of the main wheels failed. On November 13th, 1980, an electronic component failed, and control over the roll wheel was lost. The wheel itself was still fine, they just couldn't control it, and it shut down. Okay, this is not ideal, but aerospace engineers are a clever bunch, and I'm sure they can figure out how to... 9 days later, they lost the yaw wheel. And 19 days later, they lost the pitch wheel. In less than a month, Goddard's new spacecraft had lost all ability to orient itself with the reaction wheels, and was left with only the magnetic torquers for attitude control. Magnetic torquers are super cool, but provide far less control authority than the wheels. Basically, they are electromagnets that play off of the Earth's magnetic field to impart torque onto the spacecraft. No moving parts and no propellant usage, but they're very weak. Practically overnight, SMM's pointing precision went from less than an arc second to 15 degrees. That's about 54,000 times worse. This was very bad. Some of SMM's instruments could keep gathering data, but several were completely unusable with such sloppy pointing. Normally, this is where a mission would resign itself to operating at a fraction of its capacity and just try to make the most of the situation. But the spaceflight landscape had changed recently with the introduction of the Space Shuttle. In the 1970s, Goddard Space Flight Center started an initiative to make satellites more standardized and thus, hopefully, cheaper and faster to build. What resulted was the Multi-Mission Modular Spacecraft Bus, or MMS. This was a sort of starter spacecraft that handled power distribution, data processing, and attitude control. All you needed to bring was your own antenna and the specialized sensors for your mission. What makes this relevant to our story is that once the space shuttle was approved, on-orbit servicing capability was added to MMS. All NASA needed to do in order to fix Solar Max was to pop off a box full of attitude control electronics and attach a new one. That's it. Do that and Solar Max would be back to its full capability. So in a nutshell, here's the plan. Challenger would rendezvous with Solar Max, stopping a couple 100 feet away and station keeping. An astronaut in the MMU would jet over to the slowly spinning spacecraft and use a specialized device to grab onto SMM. Once docked, the astronaut would use the MMU to de-spin the spacecraft and then back away. Challenger could then move in and use the robot arm to grapple the now de-spun satellite and place it into a cradle mechanism in the payload bay. Astronauts would then replace the electronics box and wait as the ground made sure that everything worked all right. After that, the robot arm would gently deploy SMM and Challenger would back away. All done. Even on paper, this wasn't the easiest operation, so the crew better be up to the task. That crew consisted of 5 astronauts, including 3 mission specialists, with 4 of the crew being rookies. Commanding the flight would be our good friend Bob Crippen, who we know from STS-1 and STS-7. This marks his 3rd of 4 spaceflights. Flying alongside Cripp as pilot was Dick Scobie. Francis Scobie was born on May 19, 1939 in Cle Elum, Washington. After graduating high school in 1954, he joined the United States Air Force, starting his career as an engine mechanic. While working as a mechanic, he took college courses at night, eventually being selected for the Airmen's Education and Commissioning Program. He later earned a bachelor's degree in aerospace engineering from the University of Arizona. He learned to fly and served in a combat role in the skies of Vietnam. When he came home, he entered the Air Force's Research Pilot School at Edwards, where he later flew a variety of different aircraft. He joined NASA as part of the class of 1978, and this is his first of 2 spaceflight assignments, with his second being STS-41L. Mission Specialist 1 was Terry Hart. Terry Hart was born on October 28, 1946 in Pittsburgh, Pennsylvania. He earned a bachelor's degree in mechanical engineering from Lehigh University, a master's in mechanical engineering from MIT, and a master's in electrical engineering from Rutgers University, though that one came later. In between MIT and Rutgers, he joined the Air Force Reserve, learning how to fly and then tooling around in F-106 interceptor jets around the country. He worked at Bell Labs for 10 years, putting his technical education to use and picking up a couple of patents. He was selected as an astronaut in 1978, and this is his only spaceflight. Mission Specialist 2 was Ox Van Hoften. James Van Hoften, not sure where Ox came from, was born on June 11, 1944 in Fresno, California. He earned a bachelor's degree in civil engineering from the University of California, Berkeley, a master's degree in hydraulic engineering from Colorado State University, and a PhD in hydraulic engineering also from Colorado State University. Between the master's and PhD, Van Hoften joined the U.S. Navy, who taught him how to fly. With the Navy, he flew a variety of aircraft and participated in 60 combat missions in Southeast Asia. He joined NASA in 1978, and this is his first of 2 spaceflights. And last but not least, Pinky Nelson. George Pinky Nelson, another mysterious nickname, was born on July 13, 1950 in Charles City, Iowa. He earned a bachelor's degree in physics from Harvey Mudd College and a master's degree and PhD in astronomy from the University of Washington. He joined NASA in, you guessed it, 1978. This applies to some other class of 1978 astronauts that we've mentioned, such as Sally Ride, but it just occurred to me that Pinky's first job out of college was astronaut, which, wow, well done. This is his first of 3 spaceflights. The launch was pushed back by 2 days to fiddle with the thermal protection tiles on one of the OMS pods, but it was the only delay. On April 6, 1984, the countdown proceeded smoothly, and at 8:58 a.m., Challenger lifted off for the 5th time. Today's trajectory would be especially noteworthy, because for the first time the shuttle would be flying a direct insertion ascent. Normally, right after main engine cutoff, the orbiter would actually be a little short of its target. An ohms burn would raise its orbit that last little bit to ensure that it didn't just follow its external tank back into the atmosphere. And then a second burn half a revolution later would raise the shuttle's perigee, the low point in its orbit, completing the insertion. This time, when Challenger reached MECO, thanks to the new launch trajectory, it would already have the correct apogee, the high point in its orbit, and thus wouldn't need to fire the ohms engines right away. Instead, it would only need one ohms burn half an orbit after launch, which again would raise the perigee, settling Challenger into its final orbit. Ascent is always an intense phase of flight when everyone is paying extra close attention, keeping an eye out for any developing anomalies. And this would especially be true on this first direct insertion flight. So of course, immediately after lifting off, the computers at Mission Control in Houston crashed. Not great, but this is why we have backups, so they switched over and the backup system also crashed. For an hour, all Mission Control could do was talk to the crew. They had no data, no computers, nothing. Not a great start to the mission, but Challenger arrived safely in orbit, so no harm, no foul, I guess. The first major event of the flight was on day 2 when the crew deployed the Long Duration Exposure Facility. The deployment went smoothly and... Oh, what's that? What's the Long Duration Exposure Facility? Yeah, I guess with everything else going on, I neglected to mention that this flight also carried a new specialized payload. Alright, let's get into it. The Long Duration Exposure Facility, or LDEF, is another one of these ideas that seems familiar to us now, because its role has been taken on by stuff like CubeSats and the International Space Station. A common problem confronting spaceflight engineers is that the space environment is super harsh and super weird. Materials and electronics don't always behave how you might expect them to when exposed to stuff like alternating cycles of extreme heat and extreme cold, atomic oxygen, and cosmic rays. So it's helpful to just be able to stick something in space for a while in order to examine it later on. This is part of the reason why the Apollo 12 crew cut the camera off of the Surveyor 3 probe and brought it back home. Engineers on the ground knew what the camera was made out of and could inspect it after it spent a long time in space and see how it fared. The LDEF was a satellite that would facilitate these long-duration exposures to space, hence the Long-Duration Exposure Facility. The satellite itself was pretty simple. It had no solar panels, batteries, fuel cells, or any other way of generating or managing power. It had no active attitude control system, no propulsion system, and no onboard computers. It was just a big inert structure comprising a 30-foot long, 14-foot diameter cylinder. Well, not quite a cylinder, it had 12 sides, making it a dodecagon. Or I guess more properly, a dodecagonal prism since it's 3D. Hey, on a side note, how often do you get to say dodecagon or dodecagonal? Anyway, where were we? Right, the LDEF. Each of the 12 sides of the spacecraft were split up into a bunch of trays of standardized sizes. They were all 50 by 34 inches across, and you could choose between a depth of 3, 6, or 12 inches. There were 6 trays on the Earth-facing side, 8 on the space-facing side, and 72 around the edges, making 86 trays in total. Real quick, just to help the metric users out there, LDEF was about 9 meters long, 4 meters in diameter, and the trays were 1.3 by 0.9 meters across, varying in depth from about 7.5 centimeters to around 30 centimeters. Now wait a minute. If there was no active attitude control system, then how did it have an Earth-facing and space-facing side? That's because when the STS-41C crew deposited LDEF in its orbit, they were very careful to leave it oriented with the long axis pointed towards the Earth. They were also very careful to not impart any rotation on it as they backed away. LDEF would remain in its desired orientation by relying on gravity gradient stabilization. We actually talked about this before, way back when we talked about the Gemini tether experiments in the 60s. A gravity gradient stabilized spacecraft takes advantage of the fact that one end of it is slightly closer to the Earth and one end of it is slightly further away from the Earth. That means that the two ends are really in slightly different orbits. The top wants to go slower and the bottom wants to go faster. When all the forces are balanced out, as long as no other forces are there to overwhelm this gentle nudging, it'll orient itself with the long axis pointed up and down with respect to the local horizon, which is exactly what we want. The LDEF trays were filled with experiments studying materials and structures, power and propulsion, science, and electronics and optics. And with the cost of flying a tray ranging from as high as around $1 million to as low as $25,000 in 2019 dollars, long-duration space experiments would suddenly be well within reach for people in industry and academia. The plan was that it would be chilling out in orbit for the next 10 or 11 months until another shuttle came to get it, so we'll be seeing LDEF a little bit down the road. Maybe a little longer than we expected, but we'll get there. Flight Day 3 was the big day. Under the careful control of Crippen and Scobie, Challenger eased up towards the solar maximum mission and began station keeping around 60 meters away. Nelson and Van Hoften suited up and headed out into the payload bay, with Nelson then donning the manned maneuvering unit. Once everything looked good to go, Nelson used the MMU to putter out of the payload bay and slowly fly over to the SMM. By this point, the folks at Goddard had coaxed the spacecraft into a pretty reasonable rotation, 1 degree per second along the roll axis and 0 along pitch and yaw. Nelson's task was to stop that spin entirely so that the spacecraft could be snagged with the shuttle robot arm. He would accomplish this by grabbing onto a trunnion pin on SMM. The trunnion pin was bigger than the word pin would lead you to believe. It was less of a pin and more of a short, load-bearing pipe a couple of inches long and an inch or so across that they'd use to move the spacecraft around when it was still on the ground. Attached to the front of the MMU was a device called the T-pad, or Trunnion Pin Acquisition Device. This visual isn't quite right, but it'll give you the right idea. You can imagine the T-pad as a bear trap for satellites. Nelson would place the T-pad over the trunnion pin, and when the pin hit the back of the T-pad, steel arms would clamp down around it, hence the bear trap analogy. And this is where the mission had its first serious snag. The T-pad wouldn't fit. Nelson bumped up against SMM and just bounced right back off. He lined up and tried again and bounced right back off again. Nelson went in for a third try using more force and met the exact same results. This was a problem. For one thing, it was a problem that the T-pad wasn't working as expected. But it was even more of a problem that now SMM was rotating more than it was before, and that rotation was now around all 3 axes. 0.45 degrees per second roll, 0.65 for pitch, and 1.2 for yaw. That might not sound like much, but at this point, SMM was essentially tumbling out of control. This made capture borderline impossible, but it also meant that SMM wasn't keeping its solar panels pointed towards the sun, which meant that it wasn't generating power, which meant that the clock was ticking on its battery. Run out of battery, and you lose the spacecraft. This is when the crew started to get creative. Crippen suggested that Nelson make his way up to the solar array, grab onto it, and try to use the MMU jets to stabilize Solar Max. Presumably before the Goddard engineers could gasp and exclaim, "No, no, 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 no," into the voice net, that's exactly what he did. After getting a good grip on the solar arrays, he activated a special attitude hold mode in the MMU. This mode was designed to help de-spin SMM once the T-pad was securely attached to the trunnion pin. But by activating it way out on the solar array, the MMU jets had a lot more leverage and started to make the problem worse. Over the next few minutes, Nelson continued to wrestle with the spacecraft, marginally improving the situation, but still leaving it tumbling. 11 minutes after he first made contact, and with his MMU propellant running low, Nelson returned to Challenger. Crippen then brought Challenger in so that Hart could attempt to capture SMM with the robot arm, but despite several attempts, he was unable to capture the gyrating spacecraft. Since this clearly wasn't working, Challenger backed away into a different orbit while a new plan could be cooked up. While they do that, let's take a quick look at what happened with the T-pad. Again, the plan with the T-pad was that it would fit over the trunnion pin, which would then hit a surface in the back, causing some steel arms to clamp down around the pin. This is just me speculating, but since the pin only stuck out about 3 inches, I'm guessing that the T-pad was designed to grab the full length. But this meant that the clamps would be swinging pretty close to SMM's main body. And this is the heart of the problem. Because sticking out of SMM's main body, by only a few millimeters, was a grommet. This grommet was not in the original blueprints and was not supposed to be there. But there it was. After all of this planning and testing and engineering, this one stupid little grommet followed up the whole process. Yet another example of how space is hard. Every little thing can and will get you. Incidentally, I don't know if this was common practice back in the 80s, but I know for sure that these days satellites will be extensively photographed both during and after assembly. This way, if there's any question as to what was actually built, regardless of the plan, there's something to refer back to. While Challenger backed away from SMM, engineers at the Goddard Space Flight Center got to work. Solar Max was tumbling out of control, was losing power, and had very, very little attitude control authority. And not only could they not control their attitude, they couldn't even be totally sure of what it was, since the onboard sensors were not big fans of all of this tumbling. The solution, from what I can tell, was a sort of a Hail Mary, a risky last resort move. They uploaded a new attitude control algorithm called -B dot, which, if you speak engineering, does exactly what it sounds like. And if you don't, it refers to the opposite, minus, of the magnetic field vector, B, as it changes over time, dot. The -B dot mode basically just set the magnetic torquers to do the opposite of whatever the local magnetic field was. For an analogy, if you imagine a wrecking ball swinging back and forth, -B dot would be like gently pushing in the opposite direction of the swing. Eventually, you'll slow the ball down and it will stay in the center. The catch, and the reason why I call it a Hail Mary, is that while you'll stop the spacecraft from tumbling, you'll also end up in a random attitude. And you better just hope that you end up in an attitude where your solar arrays are at least partially pointing towards the sun. Fortunately for all involved, that's exactly what happened. Tumbling stopped, Goddard managed to get SMM back into a well-behaved roll, and waited for Challenger's return. Meanwhile, the Challenger crew had problems of their own. Between the initial rendezvous, attitude maneuvers to keep Nelson and SMM in view, and hopping to a different orbit once the capture attempt failed, the orbiter was running low on propellant for its small RCS thrusters. These were used to both change which way the orbiter was facing, as well as execute small orbital maneuvers like you'd use when performing a rendezvous. The real problem was with the forward RCS module. Since the RCS thrusters and OMS pods ran on the same type of fuel, it was possible to transfer some OMS fuel to the rear RCS modules. Not so with the forward RCS module in the orbiter's nose. If the forward RCS module ran out, there'd be no way to refill it. The crew had to be especially careful since the RCS thrusters were needed to get to the correct attitude to perform the deorbit burn and to maintain the proper attitude during the first phase of re-entry before they got to thicker air and the aerodynamic surfaces could take over. In short, Challenger was running on fumes, and returning to SMM was going to be a very delicate procedure. Ground controllers did the math and came up with an approach that used slightly less propellant. This is getting pretty far in the weeds, but the biggest difference seems to be that they arrived on the V-bar 200 feet away from SMM instead of the 800 feet used previously. This led to fewer V-bar hops, which saved propellant. To give you an idea of just how close they were on propellant usage, engineers on the ground crunched the numbers and told Crippen that he could safely run down to 0% on the propellant gauge. Measuring how much fuel you have in space is actually pretty tricky, so they tend to be fairly conservative on stuff like fuel gauges. So Houston determined that if Crippen stopped at 0%, there would actually still be enough remaining to safely come home. With both Johnson Space Center and Goddard Space Flight Center each working their side of the problem, the result was that on Flight Day 5, Challenger arrived next to SMM again, which was now rotating at a leisurely half a degree per second on the roll axis. With Hart at the controls, the end effector of the remote manipulator system closed in on the SMM trunnion pin. At the moment of truth, Challenger was out of communications range, but at the next acquisition of signal, Crippen called down, "We got it." Now finally captured, SMM was lowered into a mechanism in the payload bay that would securely hold it while the astronauts got to work. After all the difficulty of getting SMM in place, the operation to actually swap out the attitude control box only took 45 minutes. The modular and serviceable satellite bus concept had worked. Since they had come all this way, a few other minor upgrades and repairs were made to the satellite, as well as some observations on how it seemed to be holding up in the space environment. In the end, all repairs were completed in only about 4 hours, leaving the EVA crew time to perform some extra tasks, such as Van Hoften's own turn in the MMU. Solar Max was carefully released from the RMS, free to fly on its own again. Some care had to be taken with the onboard software, since despite what you might think, satellites are actually pretty dumb. They had to watch out for stuff like the onboard sun sensor latching onto the big white shiny spaceplane hanging out nearby and thinking, there's the sun. But when Goddard finished its initial checkout, everything looked great. Solar Max was put through about another month of checkout and calibration just to make sure everything was good to go, and it returned to the science mission that it had been so rudely interrupted from 4 years earlier. The mission continued to return a wealth of scientific data for another 5 years before burning up in the Earth's atmosphere, its mission complete. Back in our current timeline, STS-41C's trials were not quite yet complete. When the crew strapped in and prepared to deorbit, the mercurial Florida weather refused to cooperate, and the landing was kicked back 1 rev, this time aiming for Edwards. 6 days, 23 hours, 40 minutes, and 7 seconds after lifting off, Challenger touched down, a day later than planned, thanks to the unexpected second rendezvous. STS-41C was a really cool mission that once again checked a number of boxes, proving out critical shuttle capability. On this one mission, we got direct ascent, a new low-cost method of flying long-duration space experiments, the first shuttle ground-up rendezvous, and the first on-orbit repair of an uncrewed satellite. Along the way, both Goddard and Johnson worked together and brought their respective strengths to the table, and not only successfully handled an unfolding crisis, but paved the way for decades of satellite servicing to come. Next time. Well, after this action-packed mission, STS-41D better have something crazy on tap to get our attention. What could they even have? 4,000 bees? No bees. But how about a big fire on the launch pad while the crew was on board? An invisible fire. Okay, this we need to know more about. Ad Astra. Catch you on the next pass.